Hi guys, Stupid Simple here, where I take topics that make me feel stupid and try and make them simple. Today, I'll be covering differentiation and more specifically, the chain rule. So, the chain rule is the first major topic after the power rule in the series of differentiation for roughly a high school level. We've covered the power rule, and today we'll be looking at the chain rule, and in the next video that I post, I'll be looking at the product rule. I mention these three things now because if you're not comfortable with the power rule, we're going to be making a lot of use of it in this video here. So I'd recommend checking out that video ahead of time if you're not overly comfortable with differentiating things relatively quickly, i.e. knowing that x squared differentiates to 2x. If you can see that quickly, that's fine, carry on. If not, then probably look at that first and then come back here. Today we're going to be looking at the chain rule, and that's our focus for today. But I mentioned the product rule as well because it bears mentioning first that these two techniques are useful in what seem like similar situations, although they are very different, and I just want to make the difference between them known right away. So the chain rule is the rule that we're going to use to differentiate multiple functions that are composite with one another. Now, what I mean by composite is if we have some function f of x and another function g of x. For the chain rule, we're going to apply them if we have something like f of f acting on g of x. I'll give some more definite examples in a second, but I just kind of want to make things a bit clearer now. In fact, let's do one step more than that. Let's say we have in blue, we have some function f of x, and in red, some function g of x. So, for the chain rule, what we are looking to see is the function f acting on the function g of x. And for the product rule, we would expect, let's put it in for consistency. For the product rule, we would expect to see the function of f of x multiplying the function g of x. Now, these two things are clearly different from one another, but in the field, in some examples, they may look a bit more similar than they are now. So I just want to point that out at the very beginning. This video is focusing on the chain rule here and not the product rule here. But that's fine. I'll make things a little bit more obvious as we go through. So I guess the first thing to make more obvious is what on earth do I mean by a composite function? How can there be a function inside another function? Well, let's take an example of that. Let's call f of x equal to x squared, and let's call our g of x equal to, let's say, x plus 3. So let's say f is blue and g is red. Doesn't matter, just for color coordination so you can see easier for yourself. What if, however, I were to apply this f of x function, x squared, to the g function x plus 3? Well, what that would look like would then be x plus 3 squared. If we consider x plus 3, the g function, to be just x, then when you square it, i.e. apply the function f of x, then the whole thing together squared, x plus 3 squared, looks like this. This is exactly g of x being applied by f of x in this example. So here we have f applying on g of x. Okay? So this is an application of the chain rule. Now if we want to differentiate this, because that's what this series is about, we are going to use the following definition. d by dx of some function f acting on some function g of x, a lot of brackets, equals f prime acting on g of x, all of that multiplied by g prime of x. So we have f prime, so the derivative of whatever the f function is, multiplying, oh sorry, not multiplying, acting on the function g of x, then multiplying by the differential of g of x. So let's run through this example here. Let's take our f of x is equal to x squared, and therefore our f prime of x is equal to 2x. Similarly, our g of x is equal to x plus 3, and so our g prime of x is equal to 1. Nice and simple. So, if we apply the definition, let's give ourselves a little bit more space over here, we are going to be applying f prime using g of x. Since f prime is up here as 2x, we're going to swap this x for whatever g of x is, which in this case is x plus 3. So, f prime of g of x is 2x plus 3. We're then going to multiply this, because that's the next step in here, by g prime of x. G prime of x is 1. So this term gets multiplied by 1, which just equals 2x plus 3. Clear of that. And there we have it. That is the chain rule applied. Just for the sake of checking that this works, we can actually do things a bit more manually. We can evaluate the original term that we were given, which is x plus, oh goodness, which is x plus 3 all squared, and that is equal to x squared plus 6x plus 9. Binomial expansion. If you're not comfortable with that or don't know where I got that from, let me know. I'll do a video. And we can differentiate this using the power rule. We can see that x squared goes to 2x. We can see that 6x goes to 6. And we can see that the 9 disappears. Similarly here, if we multiply 2 by x, and we multiply 2 by 3, we would get 2x plus 6, which is the same. In this case, the chain rule has worked. You can do as many examples similar to this as you like to convince yourself that this is correct, but I promise you this is how the chain rule works. Let's move on. Let's make things a little bit trickier. What we're going to look at now is something that's more obviously something that more obviously uses the chain rule, although it may not be so easy to differentiate at first glance. We're going to involve some trigonometric identities. Bit of trick. I'll do a completely separate video on their differentiations and integrations alongside some other specific things in the future. But for now, just take my word for it that stuff like cos of x differentiates to d by dx there. Cos of x differentiates to, say, minus sine x, which itself differentiates to minus cos of x, etc., etc. It's a full. Well, there's actually only one more link in the chain. The minus cos goes to sine, which then goes back to cos. But yeah, I'll do a full video explaining why this is the case soon, but just trust me for now, this is how this one works. And we'll look at another example. Let's say we have a big curly line. Say we have cos of x to the power of 4. So the first thing, if you remember my lesson on my video on the power rule, is we're gonna organize things. We're gonna take things one step at a time. So we can see here that x to the 4 is being acted on by cos. And to stop confusion from how I labeled things before, I suppose I should put x to the 4 in red and cos in blue. Because we have cos acting on x to the 4, we have some function f acting on some function g of x. You follow my logic? So in this case, we can call f of x equal to cos of x, and we can call g of x equal to x to the 4. Now that we have these, let's just quickly write down our differentials. F prime of x equals, as I said, up top. Differential of cos x is minus sine x. And the differential of x to the 4, g prime of x equals 4x cubed. Now we have all these in place. Let's go ahead. We know the definition that that's meant to be a d, that d by dx of f of g of x bracket 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 equals f prime of g of x multiplied by g prime of x. So let's find it. F of x is cos x, f prime x is minus sine x. So we have minus sine acting on g of x, and in this case g of x is x to the 4, you'll remember. So our first term is minus sine x of x to the 4, and that is then being multiplied by g prime of x. G prime of x is 4x cubed, and that's it. We can rearrange a little bit for sake of neatness to minus 4x cubed times sine of x to the 4. But that's the same idea. This is how the chain rule works. We have two things that are acting on one another, or two things, one is acting on the other, and we apply the definition. And that's all we have to do. I'm going to show you an alternate notation now, but I promise you it means the same thing, and we'll run through the logic in the exact same way. Now I think is a good time to go through some slightly harder examples and look at some more specific tricks that you may come across, and just go through some general errors and things that may be commonly seen that will give you the wrong answers, and we'll try and correct those and smooth those out as best as possible. So we're going to start with the function, let's call it y equals, and let's say we're going to work out the square root of x squared minus x. Now, I would thoroughly recommend you give this a go yourself first, but if you can't or if you get stuck, that's absolutely okay. Take a couple seconds now, I'll wait, and I'll be back in a few. Okay, perfect. If you've given it a go yourself, brilliant. If not, that's okay. Let's go through it together. First things first, we're going to separate our functions f of x and, oops, first things first, we're going to separate our functions. F of x is the square root of x, which is equal to x to 1/2. And therefore we can see quite comfortably that f prime of x is equal to 1/2 x to the power of minus 1/2. And our function g of x is equal to x squared minus x. And therefore we can see that g prime of x is equal to 2x minus 1. If you'll recall the definition again, d by dx of some function acting on some function of x is equal to the first function f, or the outside function f prime, applied to the same function, g of x, multiplied by the derivative of the function being impacted, g of x, g prime of x. Therefore, we have f prime over here, so therefore we'll take our 1/2 x to the minus 1/2 down here, but instead of the x, we're going to be applying g of x as stated here. So that will give us 1/2 of x squared minus x to the power of minus 1/2. That's going to be multiplied then by g prime, and g prime we have right up here. We don't need to worry about anything fancy with that, we're just going to simply multiply. I'll put it in a bracket because it's separate and we don't want to be confused about what's multiplying, what's not. So we're going to multiply by 2x minus 1. And that's technically everything. Now we can simplify this a little bit. We can start by saying, okay, 1/2 times by 2x gives us x, and 1/2 times by minus 1 gives us minus 1/2. So let's do that. So our coefficient for the whole equation is going to be x minus 1/2. And then our index, or our indice, is then going to be x squared minus x to the power of 1 to the power of minus 1/2. If you remember index notation, minus means it's something over the top, and to be at the power of 1/2 is to be square rooted. And since this is how fractions work, we can put the x minus 1/2 over top, and that will give us x minus 1/2 over square root of x squared minus x. Okay, it's a pretty annoying final answer, but it's, the steps to get there are not horrific. It takes a minute to think about it and to look through it, but go through this once or twice, apply the steps one at a time, think about why we're applying them, and think about, honestly for me, and this is a personal opinion, but the most important step is absolutely setting up f and g at the very start. Knowing what f and g are, and knowing what the derivatives are, makes life significantly easier. If you can say what's acting on the other function, and you can find both of their derivatives individually, then finding the derivative together becomes so much easier. So to recap, in this case, we saw that the function x squared minus x was being acted on by the function square root of x. We differentiated both of those individually, and that gave us our f prime and g primes over here. And then we could simply apply the definition before. We see that the derivative of the square root function over here is 1/2 x to the power of minus 1/2. Swapping that x, this specific x here, for the function g, as we follow along this snaky trail I drew earlier, we get exactly all the way down here this function, all of this. We then look at the second part of the definition, g prime of x, and that's just a simple multiple. We throw that in, so you clear things up a bit so things are a bit easier to see. And we have a multiplication. And that's all there is to it. I times the multiplication by the half because coefficients are nice like that. And then I put everything over to the top to make things neater and put everything as one term. And that's all you've got to do. Let's look at another example and then we'll call it there, I suppose. Let's consider y equals cos of sin x. We're going to use the exact same rules as before, even if we have multiple weird things to work with. So first things first, what's acting on what? Cos is acting on sin, or sine, depending how you pronounce it. Therefore, f of x equals cos of x. G of x equals sine of x. We'll differentiate those individually so that we have f prime of x equals minus sine of x. And g prime of x equals cos of x. We have all of our individual differentials ready, so let's apply the definition. d by dx of f of g of x equals f prime of g of x times g prime of x. Once again, we consider our f prime of x, which in this case is minus sine of x, or at least minus sine, but inside that we're putting g of x. This one right here. Let's do red. So inside our sine, we imply g of x, which is sine. So and we're going to multiply this by g prime, and g prime we have pretty comfortably is just cos of x. And there we have it. We have minus sine of sine x cos x. It didn't get simpler, it got harder, but that's okay. These things don't necessarily have to get smaller or bigger whenever we differentiate them. This is just how it works. Again, we'll go through our individual steps, but I hope the methodology is relatively clear to you. We see that we have a composite function, a function that has something acting on something else. Acting, not multiplying, is the important takeaway here. We find the individual functions, and we find their individual differentials. We find f, we find f prime. We find g, we find g prime. We then go to our definition, over by here. If you don't have that memorized, that's absolutely fine. You may be able to find it in textbooks, or you may be given it in an exam. But if it's not given, it's a relatively simple thing. There's only 3 things you need to remember, although they are quite similar, and I will grant you they can get confusing at times. Inside the definition, the only things to remember are that you use the f once at the start, f prime, and inside of that goes g. Outside of that goes g prime. Okay? So f prime acts on g, and the whole thing is multiplied by g prime. That is how the definition works, and that is how the chain rule works. If you have any questions, if any part of this doesn't make any sense, or if I've skipped over something that you're not overly comfortable with, or if you'd like some more examples, please tell me. Let me know down in the comments. The next video I plan to release is on the product rule, but if there's anything in the meantime that you'd like to know, please tell me. So that's the chain rule. I hope it made sense, and I hope to see you again in the next video. But most importantly, I hope you found that simple, right?